As an architectural CFD fluid dynamic expert, Mr. CFD offers various CFD products in an architectural field. With the help of CFD modeling, AEC industry engineers are able to carry out the validation of HVAC systems and components, predict wind loads, optimize thermal comfort, control air quality and pollution, and improve energy efficiency. This CFD training package includes 10 architectural CFD simulations from the CFD shop that engineers can purchase and use as a template for their CFD analyses from various architectural systems and components as an architectural CFD training package. By clicking on the subscribe button, you will be informed about the newest CFD training videos by Mr. CFD. Or if you are watching the training video, click on the Mr. CFD logo and subscribe. The present problem simulates the airflow through the space between the two walls of the double facade of the building considering solar radiation. The mesh display dialog box controls the display of zones, surfaces, and partition boundary meshes. The nodes, edges, faces, and partitions in the options section respectively enables the display of nodes, display of mesh edges, and mesh faces, and even display of partitions. Options contains the rendering options. To see the effects of your selection, you must click the display button. The boundary condition for inlet, the type of boundary condition is pressure inlet. The pressure is equal to the atmosphere pressure and 1 atmosphere, and temperature in the pressure inlet assumed to be equal to 300 degree of Kelvin, and about the radiation. Contains the boundary conditions for the radiation model at the pressure inlet, external black body temperature method, and internal emissivity set the radiation boundary conditions when you are using some radiation models, including discrete orientation or DO, for radiation heat transfer. Also, the participates in solar ray tracing option specifies whether or not the pressure inlet participates in solar ray tracing. And about solar transmissivity factor specifies a multiplier ranging from 0 to 1 that is applied to the solar irradiation entering the domain through the pressure inlet. The shading plates assumed to be adiabatic, so the heat flux is activated and heat flux magnitude is equal to 0, and also the material name is aluminium because the material of the shading plates is assumed to be aluminium. Finally, we can check the mass flow rate from the outlet boundaries. The magnitude is the minus, and the reason is because it's mass flow outlet, and we see that the effect of buoyancy flow, and it leads to the air go outside from the facade chamber, and with this mechanism we can have a good ventilation system, and it's also a passive ventilation system. Finally, this table is a summary of the steps for defining the problem and its solution as a review. The second problem is simulating the HVAC inside the room considering a solar chimney. In the cell zone condition, we should identify an energy source as a heat source in the glass zone that is equal to 15,000. In the report section of the results, we can choose the surface integral and identify the area weighted average, and by specifying the field variable we can display and investigate and study all of the parameters in all the boundaries. For example, to check the pressure drop from inlet zone to the outlet zone. For example, to check the velocity at the inlet, at the outlet, and every point of the domain, and also the temperature, and every variable could be obtained in this section. And also the diagram of temperature distribution in the transverse direction at the point in the middle of the solar chimney, I mean the left figure, and the graph of velocity change in the transverse direction in the chimney outlet section, I mean the right figure, are obtained. Finally, this table is a summary of the steps for defining the problem and its solution as a review. The third problem simulates the airflow of air inside a room, considering a heater and checking the heat transfer inside the room by single-sided ventilation. The next problem simulates the wind flow through 3 tall buildings arranged in a triangular shape. For setting under relaxation factors, we should say that the pressure-based solver uses under relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under relaxation factors initially. It is good practice to begin calculation using the default under relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under relaxation factors. Occasionally, you may make changes in the under relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under relaxation factors too much. A cautious approach is to save a data file before making any change to the under relaxation factors, and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitude, you should consider halting the calculation and returning to the last good data file saved. The velocity contour. A summary of the steps for defining the problem and defining its solution is given in the following tables as a review. The problem number 5 simulates the heat transfer inside the interior of a mosque considering radiation.
In the appeared window, we enable the energy equation since we want to know the temperature distribution in our computational domain. By clicking on the radiation tab, you will see that the BC type for this boundary is defined to be opaque, since no solar rays enters from this boundary. Now, for example, we want to show velocity vectors for this plane. In order to do that, we need to click on vectors and accept the appear dialog box, and then in the appear window below, in the below section, in front of the location section, we can select the defined plane. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
The problem number 6 simulates change in the mass fraction of carbon dioxide on an urban street over time. All the walls in this computational domain are a stationary wall with no slip. Also, in this way, we can check the two-dimensional mass fraction of CO2 as a species. Finally, this table is a summary of the steps for defining the problem and its solution as a review. The 7th study examines the performance of fan-driven airflow inside an office for HVAC operation, including a computer and 4 lamps. The heater wall has the coupled temperature boundary condition, thermal boundary condition, because it has a connection in both sides of the inner and the outer with the fluid. And here we can see the two-dimensional temperature contour, that the maximum temperature is equal to 317 degrees of Kelvin in the center of the computer. Here is a summary of the steps to define and solve the problem as a review. The problem number 8 simulates the external airflow through an atrium. And the next project simulates the internal airflow inside an atrium located in a complex.
As for the out ORG boundary, you will see that this boundary is on the lower part of the atrium. Also, the type of boundaries for outlet is defined to be pressure outlet. And again, by clicking on edit, we will be able to change the settings for this boundary. After creating the plane, we click on Contours button and accept the appeared window, and then in the location section we click on the plane and we can select the variable, which in this slide will be pressure. Now in order to create a 3D contour, you just have to click on volume rendering button and accept the appeared window, and then under the detail of volume rendering you just have to select the variable you desire. For example, in this slide we selected pressure and then click on apply to show the 3D contour to you. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
And finally, in the last product, we simulate the airflow and ventilation inside a wind catcher.
If you click on the outlet boundary, you can see that the type of this boundary is defined to be pressure outlet. Just like the previous slides, if you click on edit button in the appeared window, the most important point you should pay attention to is the gauge pressure, which has a value of 0, which means that our airflow exits the computational domain to the atmosphere. And finally, in this slide, you can easily see the streamlines of the airflow colliding with the wind catcher structure and how they enter the interior area of our building. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product. By clicking on the subscribe button, you will be informed about the newest CFD training videos by Mr. CFD. Or if you are watching the training video, click on the Mr. CFD logo and subscribe. To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.